Right. Yeah, so my name is Mael Guennou. I'm from the University of Luxembourg. And yeah, so this is about group theory, knowing that I come from an experimental background. So just by to get a feeling of the room here, so who is more on the experimental side of things in their work? Wow. Who? Who is more on the theoretical side of things in their work? Who is doing a bit of both? Who is doing neither? Yeah, that's what I thought. So, to our experimentalist side of the room, so this talk really, I mean, it's not a proper lecture because, of course, it would take much more time, but the aim of this lecture is really to get into this with you together, okay, and hope to convince you that this can be really useful, and try also to introduce you to this type of language that is very often an obstacle when you get to this type of field. To the theory part of the room, I'm sorry. You can go to the beach or you can beat me up afterwards, okay? So let's start briefly with a short motivation with that. So as Steve said, I come from Raman spectroscopy, from already during my master's studies some years ago. And so when I used to read papers, of course, I would read papers on Raman spectroscopy, experimental papers, and I would stumble on paragraphs like this. So primitive cell, blah, 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 so this I know. Factor group analysis yields the following modes, and with this Kabbalistic thing. So this is practically my purpose for today, to really explain what this sort of thing means, what's the background behind, and how it can be useful for us also as experimentalists. Now, this is something, and this was my experience during my whole studies with group theory, that we would start slowly with the mathematics, like, oh, this is a group, and this is how it looks like, and this is very useful for physics, but sadly the semester is over and we can't continue, okay? So all this stuff I actually had to learn by myself, which is why I developed this love-hate relationship with the topic, really, because... but again, just to prove you that it can be useful, you have a paparazzi in the room, so I know this comes from yesterday, from the first lecture that you had, if you recognize. And I don't know how much time the lecturer could spend of the symbols, but you do have notions of group theory in there, right? And you have symbols here associated to the split. Okay. So you do have group theoretical symbols that are related to the splitting of the orbitals. So this is part of also the things that we'll be talking about today. So the outline is pretty simple. I have like a little bit less than 1/2, which is really just reminders about crystallographic symmetry aspects, really. So all those are things that you have seen for sure at some point at the beginning, but maybe you have forgotten, and it's always good to go back to them. And then the second half is really what I call here elements on the theory of representations of crystallographic group, which is really what this is about. Also, I will make a huge or intensive use of this Bilbao crystallographic server. I guess many of you know it. It's been, I think, an incredible resources, both to make all those concepts really accessible and more easily usable also by non-expert, and also played, I think, a huge role in helping standardize some of the notations that we use today, at least in our community. So you will see plenty of screenshots. I won't mention it every time, but most of it actually comes from here. Before we start, I think I have a couple of disclaimers. Okay, so there's no equation in there because we don't really have time. This, I think, you will appreciate. This you will not appreciate that much. So in terms of presentation and the canonical way you should do slides, some of the slides are really bad, but I still insist of doing it this way because at least you have the full definition, which sometimes is needed because it's still mathematics at its core, so you do need the definition. And last disclaimer is, yeah, well, okay. So again, theory people, please excuse me, right? So this is going to be very hand-waving all the way. So let's get started by the typical symmetry operation, the notation that we get to use. For this, maybe because it's the morning first lecture, I would ask you to stand up if you don't mind. Yeah. So the first symmetry operation that we have typically are rotations, right? They typically note by just a number or a Cn. This is recorded. This is being recorded in case you're having it. So Cn is a rotation by 2 pi over n. So could you please do a C4 for me? Okay, so this is typically a case where, I mean, no one's doubting very much on the 90 degrees, but some people are doubting very much on which direction should I turn, right? So this is also part of the conventions that very often in the papers may not be recalled, but that are sometimes there and sometimes lead to some ambiguities. Well, for the record, it's always anti-clockwise by convention crystallography. So I will let you think about whether I have to look at yourself from the top or from the bottom. Yeah, you can sit down. The rest I will do myself. Okay, mirror plane I think is pretty easy. We'll write them M and this U I'm going to use for some specific directions. Sometimes it's also noted sigma. Inversion center, I think it's also pretty obvious, especially in our field of, I really need, do you have a stick in here? Because I really want to make love with the screen and I can't because it's noisy.
You can go to the screen now, you just can't go past halfway. You can go up to the screen, it doesn't hurt you. But if you go past halfway, it really stinks. Keep going, keep going, keep going. Yeah, I'm going to try to say something.
Oh, okay, got it. Right.
It's symmetry.
Right. I would argue this is very asymmetric. Okay, so inversion center, we write it -1 or I, very easy property. So if you consider a molecule, if there is one, there is only one. It is either unique or it's non-existent. So those are the, I think, easy one that we always have in mind. Those ones sometimes we tend to forget a bit more. Those are the improper rotation or rotor inversions. So that's the combination of a rotation plus inversion. So alternatively, in some other context, people would use rotation plus mirror plane, but let's just forget about it for a second. Oh. Thank you. This is going to be useful in more than one way. Because I plan to clean the place afterwards, what do you think? So we write it -1. So the question is, the question here is, why is this a specific symmetry operation? Because in a way, it's just a combination of two things that we already have. Now, the important thing is to realize that it is a symmetry operation in itself because it may leave a molecule invariant, even though the molecule doesn't have inversion as a symmetry operation and doesn't have rotation. So this is a typical example where if I show you this, so this is a BF3, and if I ask you what's the maximum rotation, very often the answer that comes is it's a C3, is the obvious rotation that we see, because 2 pi over 3 leaves the molecule invariant. But in fact, the higher order is a -6, because what you can do as well is to rotate by 2 pi over 6, so anti-clockwise, and then do the inversion. So this brings this atom here, and the molecule remains invariant. So the first symmetry operation for this molecule that you should consider is actually -6, and not 3, okay? So this is one that, from my experience, we tend to forget a little bit. By the way, I will also need a bit later this word on improper versus proper symmetry operations. So this one is improper because essentially it contains an inversion. Mirror planes are improper, inversions are improper, and those are improper. The other, that means essentially the rotations are proper. So this was for molecule. Then, as you have seen also in in your classes in solid state physics, if you go from molecules to infinite crystals, then you need to add a couple of things. So first, you need to add translations by lattice vector. Translations are symmetry operations because they leave your infinite crystal invariant. And then you need to add two types of operations that are a combination of one of the point operation that we've seen before, plus a translation by a fraction of the lattice vector. And there's two of them. So one is the screw axis and the other one is the glide plane. So the screw axis is like here, combination of a rotation and a translation along the rotation axis by a fraction of a lattice vector. Now, by tradition, I've been doing this lecture, I think, 3 times in this school. By tradition, I have to do the screw axis for you. So let's do a translation downwards combined with a rotation. So this would give you something like this, okay? So grand plié, if you want to do it, so like from a ballet perspective, you go to really grand plié, like to, this is, okay. This is the invert operation, okay? Now, I hope this time you recorded that one because I'm not going to do it a fourth time. Screw axis. Glide plane is the combination of a mirror symmetry with a translation parallel to the mirror plane. So as, for example, here, and this one I'm not going to do it because I'm tired already. I'm old. Okay, so those are all the symmetry operations that we have to deal with. Now, as you also remember, when we go to infinite crystals, we have a number of interesting properties. So we can't have all possible rotation, but we have this crystallographic restrictions theorem that tells us that we can only have 2, 3, 4, and 6. And we group the possible groups for possible point groups of crystals into 32 crystallographic point groups. I will come back to magnetism a bit later, and 230 crystallographic space groups. So this is all that we have for classical crystals. So I would say, I mean, in a way, for us experimentalists, this is all known, mathematical, tabulated. What we have to learn is really to navigate this ocean, right, given the various maps that are given to us. If you're not looking for crystals, but for molecules, then of course you have more than that. You need to add all the point groups for linear molecules, in which case it becomes infinite. Yes, please.
Yeah, sorry, I don't know this restriction theorem. So why can we only have these rotations?
Yeah, so let's 2 minutes. The classical way to see it, it's really something that you would find in any classical solid-state physics textbook. So the classical way to think about it is to take a series of lattice points. Okay, so those are all lattice points. And then you're saying that your lattice has some rotation as a symmetry operation. So the rotation should leave this invariant. So if you take this, for example, as the axis of rotation, so we're going to rotate here, this would bring this dot somewhere like here by an angle like theta, okay? So this should leave your crystal invariant. But, I mean, this is an infinite lattice, right? So what you are saying is that if this is a lattice vector, and let's say that you should have another lattice vector here. Let's put it, I actually don't have to. This has become confusing. No colors. Okay, so this is my first lattice vector there, and this would be my second lattice vector. I mean, you get a feeling that you can't do any rotation, right? This point has to fall onto the next line of lattice vectors, otherwise it doesn't work, okay? So then there is a bit of geometry involved, and you realize that you can actually only do that with those rotations and nothing else. That was not the best demonstration ever, but that hopefully that still gives you a feeling. Yeah, so I was saying, so for molecules, so you need to add groups for linear molecules typically, which then, I mean, then the group the group here contains an infinite number of symmetry operations because any rotation works in that case. So this modifies the mathematics a little bit. Then you can have rotations that are not allowed in crystal, like typically 5-fold and 8-fold. And I like this example very much. It's a very nerdy stuff, but I like it. I'll tell you why. So this is sulfur, okay? It's a molecule of sulfur. It has a ring, and it's not planar. It has this kind of buckling, and there's 8 atoms. So S8 is really the chemical formula of the molecule. But It's also the symbol for the symmetry operation, the rotor inversion S8. See? Because you take this sulfur here, you rotate by 2 pi minus 8, and then you do mirror plane, it brings it here. Amazing example. I love it. But this is all that we're going to say about molecule. I will really limit myself to crystals for what follows. So the list, again, I'm sure you've seen this list before of the point groups. I would like to remind you that there's typically two sorts of notations that you will find in that context. One that we call the Schoenflies notation. That's very much a chemistry and spectroscopy notation originally. And the other one, this is the Hermann-Mauguin notation, which is much more suitable for, let's say, physics, and which is also the international notation. So you will find plenty of those tables that give you the correspondence between those notations. I will be using in my examples later a lot of this one, okay, because it happens to be simple and also relevant for many of our crystals. So just briefly, in all the symbols, they contain themselves some information about the symmetry operation that you have in there. I'm not going to go into all the details of those things, but this is for the Schoenflies notation, and this is the type of explanation for what the symbol means, right? So for C again, cyclic, C horizontal, S Spiegel, and so on. I mean, obviously, this is not something you learn by heart, but this is something you end up knowing after practicing for a while. This is the first page, and this is the second page of those notations. You have it. I'm not going to comment that much on them. I'd rather much comment on that because this type of notation I am going to use. So it's good that maybe we recap a little bit. So this is in the Hermann-Mauguin type of notation, and those are the representations of all the symmetry operations of the cube. Okay. And here, what I like very much and what I am going to use is that those notations are really very explicit, and they tell you exactly which operation you're considering and around which direction. So if you take here, for example, this 4Z, so this is the C4, so the fourfold rotation around the Z-axis, not to be confused by this one, which is a fourfold rotation by the y-axis. So of course, those two are equivalent because it's a cube, right? So all the x, y, z directions are equivalent, so also the symmetry operations are equivalent. And in terms of group theory, we'll say that they are going to be grouped in the same class. But still, in real life, very often you need to keep track of which is the direction you're using for your rotation. So which is why I personally like this explicit notation very much. When it comes to labeling symmetry operation. Just some of them are really obvious. Maybe less obvious are those PQRS here that I used as a convention to denote the main diagonal of the cubes for the threefold axis. Okay, so there's going to be a couple of them. So right, I mean now we have, I think, all the notations we need. And just before we go into the real group theoretical stuff, I just wanted to give you this reminder as well, that the reason we like to classify crystals according to their symmetries is that they are, of course, related to their physical properties. I guess many of you here are working with ferroelectric crystals, so I'm 100% sure you've seen this table before that divides the 32 crystallographic point groups into piezoelectric point groups, half of which are polar and pyroelectrics, the other half being non-polar, and the remainder, so the 12, being non-piezoelectric. So this is something that I'm sure all of you have seen. This is just an opportunity maybe to make a reminder that the lack of, that there is very often a shortcut that is made for a piezoelectric crystal that says that you just need the absence of center of inversion. Sorry, so this is usually a shortcut, so this is the real table and point groups that you should consider. So this one you've seen, this one maybe you haven't seen so much. So I just wanted to bring it up very briefly. This has to do with the topic of chirality. So it's a topic that happens to be very much in fashion those days, but also very much, to my taste, a little bit confusing, because people are coming from different backgrounds and sometimes using different, say, definitions or conventions about chirality. So what I'm talking here is really only about what people would call structural chirality, so the chirality that comes from the crystallographic symmetries. I just have those 2 slides, so there will be a lot more to say, but quite frankly, if you want more, I can only recommend those 2 references here. This here is a paper in 2022 that deals mostly with this crystallographic aspect, and this one is much more recent. It was published a few weeks ago by our dear colleagues from Liège, Eric Bousquet. Also goes into the crystallographic aspects, but also much more into what this implies for physical properties. So that really, if you want to clarify your ideas about chirality, I can only recommend this paper. It's really, really good. But okay, so briefly again, the question here is, can I classify crystals as chiral, as non-chiral, just like I classify them as polar and non-polar for ferroelectrics? This is what we are trying to do. And the answer is yes, but it's not as simple as for polar groups. The first thing to note is that if you address chirality, you have to consider the space groups. So considering the point groups only leads you nowhere. You do have to consider the space groups. And the definition would be the following. So a crystal is to be considered chiral if its space group contains only proper operation. So if you remember what I said earlier, that means no inversion, that means no Mael plane, that means no roto-inversion, nothing of the sort, okay? Having said this, there is still a distinction that we need to make, and that at first sight is a bit twisted. So here we start with, merci. Here we start with our 230 crystallographic space groups, which we want to classify. And you see that this goes into 2 branches and that there's 2 different notions here in blue and red. In red is really the classification of space groups. So we are talking about chiral versus achiral space groups. So this is really a classification that's based only on the symmetry element of the space group itself. And then in blue, you have what's called the chiral structure, which is the real crystal that you have. Sorry for that. And what you see on this tree is that if you take a chiral space group, you can, of course, generate chiral structure by essentially populating your space group, if you wish, with a real atomic pattern. But you can also get where am I? Yeah, you can also get chiral structures from a space group that's achiral. If you use as a base a motif something that is chiral. So this is where This is where it gets a bit confusing. So in terms of table, what you need to tabulate are those 2 types here: the chiral space groups and the achiral space group that contain only operation of the first kind, which is to say that satisfy this definition here, okay? So this is what it gives you in terms of table. Those are the 22 chiral space groups, and you see that they work in pairs, okay? So just with the first line, they work in pairs as P31 and 32. So this symbol again here, 31, 32, is for the screw axis along a 3-4 direction, and they all work the same. So here, in that scenario, those 2 space groups are enantiomorphs. They are related by each other by one improper symmetry operation. So the way that you can see it as an example would be this, for example. So this is, for example, this is the 4-fold screw axis that would correspond to either of those pairs here. So this is the screw axis corresponding to 4, 1. So if this is a lattice vector here, what you do is you move by 1/4 of the lattice vector and you do a C4 rotation. So this brings these atoms from here to there, and then you repeat a second time, repeat a third time, repeat a 4th time, and you're back to 1 lattice vector, okay? If you now take this 4, 3, this atom gets here because you also move by you move by 3/4 of a lattice vector, and you rotate by 90 degrees. Then you move again by 3/4 and rotate by 190 degrees, which is equivalent to that one, okay? And so on and so on. And what you see here is that those 2 really now look like the type of left and right-handed structure that you usually have in mind when talking about chirality. So this is the picture that corresponds to those 22 chiral space groups. And what about those then? So, well, those are also, the space group itself again is not chiral, but if you put a chiral motif in there, you can generate a chiral structure. The difference is that if you apply, say, inversion symmetry to one of those crystals, you will describe the other variant in the same space group. Okay? So this is the reason why we need to make this distinction here between those two families. Again, this is a very partial way to describe chirality because I didn't even put magnetism in there, right? Which is a shame. But if you limit yourself to the crystallographic aspect, this is what you can have in mind. And again, I highly recommend the reading of that paper. Yes?
Can you just quickly elaborate on what invariant means? Because I think you lost me there.
Oh, okay. Yeah, it's true that I didn't recall that. So invariant means that you take your crystal, or any object for that matters, you apply a geometrical transformation, and you are invariant means you remain the same. That's it. So here, here I was describing the way that the atoms are transformed, okay? But if you take this object as a whole and you apply this screw axis, it remains the same. You don't make a difference. Oh, yeah.
Then I may also just interrupt and ask a short question. Could you also please elaborate on what is the achiral first type only transformation?
So you're talking about?
Yeah, from here. Sort of.
Okay, so here they're using first kind as proper. This is just the same thing, okay? So this, what they say here, is really space group satisfying this relation, so only proper operation. So in practice, you find only, So those are the one here. What you see, I mean, forget about the lattice centering, but what you see are only rotation, screw axis, but like I said, no mirror plane, no nothing. Does that answer your question?
Sort of, I just don't understand what is the rotation. Chirality is sort of like the object in the mirror is staying the same or not, right?
Well, that's typically the kind of thing that we learn first, and that originally comes from the, say, a molecular view of chirality. Okay, so it's not untrue, but if you want to go to the classification of this phenomenon on the basis of the crystallographic space group, this is what you have to do. So what you're saying is going to be realized in all real examples of crystals made from those structures. Only if you stay only with that view, you miss that distinction. Mm-hmm.
If I can comment, so there is some subtle distinction between the words enantiomorphic and chiral. So chiral, in the sense of Lord Kelvin, which you probably refer to, a subject which has only the doesn't have the mirror symmetry of it is something. It's not the same thing. You cannot transform it back by the improper rotation. While enantiomorphic, in that sense, means that there exists the other counterpart. So you have like left hand and right hand, so you have both hands. And this theory refers to crystals, this in the sense of enantiomorphic. So whether there is two pairs. So there are two pairs either because the space group has two variants, or the space group allows to put two different variants inside.
Thank you.
Yeah, thank you. Because, like, on that topic, again, I recommend this paper, but I highly recommend reading many of them, because depending on where people come from, they write in a different way, and I still find it very confusing. And that's not even going into the notions of true versus false versus virtual versus whatever chirality, I think. Well, anyway. Okay, so this is pretty much everything I'm going to say about this topic, but I still need to say one word about magnetism. So there's not going to be a lot of it in this talk, but the question is how do we introduce magnetism in this picture? So if you introduce magnetism, what you do typically is that you introduce one additional operator that we traditionally call time inversion symmetry, and that we note 1 prime. Okay? The action of this operator is that it takes a spin or magnetic moment and flips it. Okay? So that's what it does. So typically you would represent this like that, x, y, z, and you would have a vector typically with some magnetic moment m. Now, what's important to remember is that, so this is not a polar vector, right? It's something different, so it does not transform like a polar vector. If you want to have a graphical representation of it, what you should have in mind is not this vector, it should be this loop, okay? So think about just a point charge moving and creating a moment. This is the object we're talking about. And this loop does not transform like a polar vector. So let's just do this exercise to check how these things transform. Or just before, from a pure notation point of view. So when you combine this time inversion symmetry with a geometrical operation, then you just write it with a prime. So m plus 1 prime would be m prime. So let's, how do we organize this? So this side of the room, you're going to be p, and this side of the room, you're going to be m, if that's okay. So if my p starts like this, how does it transform according to 1 prime? And for the m side of the room, how does m transform? So please vote. So again, p here, m there. So 1 prime is the time inversion symmetry. So time inversion symmetry does nothing to polarization, right? But it does flip the m, okay? This is -1, this is my inversion. Polarization goes down, but magnetization doesn't change. I mean, if you apply inversion symmetry to that loop, it doesn't change, right? So, my, so here mirror plane, y being the normal to the plane, so it's the xz plane, if you wish. You can vote. Yeah, so this one doesn't change, right? Because the polarization is in the plane, so no change, but this one changes. And finally, last one. This one doesn't change, and this one is invariant as well, okay? So this, again, as a reminder, not all arrows are polar vectors, please. So now, what happens if you add this to the crystallographic point groups that you know? Well, of course, you have many more possibilities. So typically, for the point groups, instead of 32, you're going to have 32 plus 58, and that would correspond to 3 different cases. So the first case are the groups where the time inversion symmetry does not exist at all. It doesn't leave the crystal invariant. So this is typically, think of a ferromagnet, has a magnetic moment. If you apply time inversion symmetry, you switch it, it's not invariant. So then, essentially, those are just the point groups that we have seen before. Then we have the second set, where it exists itself as a symmetry operation, so the crystal is invariant under some symmetry operation, and then, of course, it has to combine with all the existing symmetry operations themselves. So that would give you that one. So here, think of something that's paramagnetic. So there is no magnetic moment in there, so to speak, so if you apply time inversion symmetry, it's invariant, doesn't change. And then the last one are the case where it doesn't exist alone in the time inversion symmetry, but it exists in combination with some others, okay? So alone it doesn't, but it exists as, for example, m prime. And then you have to see all the possible combination that exists, and that gives you then 58 point groups and that many space groups, okay? So again, just like the crystallographic points group, if you want to find them, you can find them in Bilbao. This is what it looks like with a corresponding symbol. This is also the sort of detailed information that you can find in there. So those nice people have done the work for you so that we don't have to do it again. So here is an example for the point groups 2 prime over m with the different symmetry operations that you have. And then they directly tell you what property is allowed or not. That's very kind of them. So centrosymmetric, well, yes, it's 2 over m. So it has inversion centers, not polar, and not compatible with ferromagnetism. So just like this classification of polar versus non-polar point groups can tell you if a crystal can be ferroelectric or not, it works the same here with ferromagnetism. So you can do it for yourself. Here is another example of 2 prime / m prime. Which this time is compatible with ferromagnetism. You can do that as an exercise. Just as a final practice on that, And going back to this one, we say it's not compatible with ferromagnetism, but typically in this shape, it can be compatible with some sort of anti-ferromagnetic order, right? That could, for example, look like this. So let's imagine that this is your symmetry elements in this particular point group and that you have a spin here. We have as a symmetry operation my. So my is this plane, so it brings this spin to there, and the mirror plane, as we said, doesn't flip the spin. So this one goes there, it's invariant. Let's take this one as a last example. This -1 prime would send this spin over there and spin it because of the prime. So this picture here describes some antiferromagnetic order that is compatible with all the symmetry operations from here. Okay? How are you doing so far? So I'm done with here all the reminders and things about crystal symmetries that I wanted to mention. So now we're getting into the meat of the presentation, which is the group theory itself. And this is where you will get a lot of text, which again I'm not going to read completely. So, bam. Okay. Who has never seen that before? Oh, there's still a couple. Okay. I mean, I won't go into all the details because it's too long. I will just remind you that, yes, the group is this mathematical structure from algebra where you basically need a set of elements and an operation. And this operation has to satisfy a number of elementary properties. I would say, most important that we tend to remember is that you have some identity element, which of course is just the identity operation, the one that changes nothing. Associativity, typically we tend to forget about it, and also the existence of the inverse. So for every element we need another one. And of course what makes it usable for us is that if you take all the symmetry operations that leave a given crystal invariant, it forms this beautiful mathematical structure of a group, so we can use the relating mathematical properties. If it's the first time that you see this, then the next thing is maybe going to be even worse. So here I'm bracing. Okay, so definition of a representation. Again, I put this here so that you have it. You can read it again and think about it later, and I'm trying to give in the following slides a graphical representation of what that is. But still, I mean, it's mathematics, so we need a bit of mathematics. Underlying things, in addition to our group, when you talk about representation, is a vector space. So it's not crazy to speak about vector spaces in physics. I hope you're convinced of that. We have many common vector spaces that we use. Or, of course, quantum theory describes the states of a system in terms of vector spaces. But also for me, as an experimentalist, all those atomic displacements that I'm going to consider for my spectroscopy or for phase transitions, those are also described in vector spaces, and then all the physical properties described by tensor are also based on vector spaces. So this is just to convince that this is not esoteric, but it's really based or deeply rooted in what we do. And then having said this, what we call a representation really is a mapping. It's a mapping where for every single symmetry element, you're going to have a matrix in such a way that you transfer the group structure from this group of symmetry operation to a group of matrices. So by this I mean that this condition should be satisfied, and then based on that we have a number of important words that come from this matrix idea. So first is the dimension of a representation. It's just dimension of the matrix. The basis of the representation is the basis of the vector space that you use to write those matrices. And the character of our representations are the traces of those matrices. Okay, again, this is the words. Graphically, this is what it looks like, okay? So I'm taking something that looks like, or that is my symmetry elements for my group MM2. I have 4 symmetry operations in there, 1, 2, MX, MY. And to every symmetry operation, I will just associate a matrix, okay? That respects this. That's all that I'm doing. This is a representation. So let's take a very obvious example. It's one that is a bit special and that we call the totally symmetric representation. So what we are going to do here is that for every single symmetry operation, we are going to associate the 1-by-1 matrix that I want to fill with a 1. Okay? So pretty boring at first sight. So this is identity, 2-fold rotation, mirror plane. I have 1 for everywhere. So I will let you check that this completely satisfied the conditions that I gave before. I mean, it's completely obvious, completely trivial. I mean, clearly this is something that I can always do, right? I mean, no matter which group I have, no matter how many symmetry operation that works. The question is, does it mean anything? And yes, it does mean anything. It means that, or what we are going to say is that this is the totally symmetric representation, and that all scalar properties transform like it. So here, transform like, if there's one thing you have to remember from this talk, it's just that. So I will repeat it about 20 times until the end, because this is to me, this is the key into understanding what those objects means. Transforms like. Can you say it after me? Transforms like? Thank you. So again, all scalar properties transform like the totally irreducible representation, meaning it's invariant. Think of temperature. If I apply geometrical operation to my crystal, of course temperature doesn't change. It's invariant, meaning it is invariant by every single symmetry operation, and this is called the totally symmetric representation. Okay? Now, of course, it's not what we would call in mathematics faithful, in the sense that you cannot go back from the matrix to its symmetry element because they're all the same, okay? But we never made this a condition for a representation. So it's just a mapping. This is a perfectly acceptable mapping, okay? So again, keywords here, totally symmetric representation describes how scalar properties transform like. Now that I have those matrices, I still have to say a word about reducible versus irreducible. So here is a graphical, so here is the description, but here is the graphical representation of that. So again, I make this table here with all my symmetry operation, and I defined a representation by writing those matrices. All those matrices are written in a given basis, which again is the basis of my representation. If I can find a nice base where all of my matrices can be written in this sort of block diagonal form, then this representation is called reducible. If I can't do that, it's irreducible, and it's called an irrep. Okay? Now, if you remember your linear algebra, when you see this, you realize that what you're doing is just you're decomposing your vector spaces into subspaces, right? This is the only thing that you're doing. So this would be an example for a reducible representation. And this is now an example of 3 irreps, so irreducible, because then I can't do that anymore. I can't find any basis that makes it more simple, okay, that allows me to separate my vector space into subspaces. So what I've done here graphically is to take a representation that is reducible and reduced it into a sum of irreps. So what I'm going to write is R, my original rep, is A plus B plus C, where in principle we should use this symbol which stands for the direct sum, because I mean you realize what is behind mathematically is really just the direct sum of vector spaces. Now very often we are lazy and we just forget about the symbol, we just write plus. But typically this is what you should be using. And then following from that picture, there's a couple of obvious properties. So the dimensions of the reducible rep is just the sum of the dimensions, and the characters are also the sum of the characters. Okay? Is that clear enough? As much as it can be. Yes?
Yeah, sorry, maybe it's a stupid question, but I mean, I still have to ask you, like...
There's only stupid answers.
Perfect. So, for example, can we understand if like the matrix is reducible if we can divide it into like eigenvalues and eigenvectors as like a basis, which is simpler?
Yeah, you can see it like that. I mean, in a way, going from those big matrices R to the reduction in subspaces. I mean, from a linear algebra point of view, it's just block diagonalizing those matrices, just all of them at the same time. You don't want to do it one by one. You want to do them all at the same time. This is the trick. So from pure linear algebra, that would be it. And from the group theory perspective, it is, by definition, this operation of reducing the representation. Okay. So then this slide is again has too many text, and I'm not going through it. You can remember the title. Everything works nicely for S theorems because we are in physics and we are lazy. Okay, so you can go through all of them. There's a bunch of keywords, theorems, lemmas that you can go through. There's also this one. It's a real name, the wonderful orthogonality theorem. For some people it's wonderful. For some other it's great. I'll let you choose your church here. But anyway, if you start developing an intuition on that, the chances are that you're right. So typically, there is this thing here that if you take a random representation, it can be decomposed into a sum of your reps, and this decomposition is unique. So this is super important. So this is a bit analogous, like you take any vector and you can decompose it on a given basis. Okay. Also, the E-reps that we need, they are known. They are tabulated and they're completely independent on a particular choice of basis. This is why this thing is so strong. And also at the end, what I want to stress is that for most purposes, everything you need are the character tables, really. So you rarely need, rarely, no, but as a lazy experimentalist, you rarely need to go into the matrices themselves. The characters are enough. And here is another way that you think about it. I've mentioned the word basis very often. So again, the basis of the representation is the basis of the vector space. But it's not too much of an exaggeration to say that the E-reps of a group give you a basis, in quotation mark, that allows you to describe how things transform under all the symmetry operation of your group. So this is how you should think about it. You take an object, you take a property, you take something, and you decompose it on a basis to understand how those, or how they, or how their components transform under all those symmetry operations. So let's try. I have a couple of examples, so we'll just essentially in the next 10 minutes repeat this over and over on different examples. Just before that, I have mentioned Bilbao. I have mentioned the characters and the characters tables. There's plenty of places where you can find them, but again, I tend to pick them from Bilbao very much, and this is what they look like, again, from my favorite point group MM2 that I've been using all the way. So what do we have here? We have the point group symbol. MM2 is Hermann Mauguin, C2V, Jean-Yves. They are nice. They give you both. Then here you have a label for the E-rep. So this one follows a convention that's a Mulliken symbol. I'll go back to it also in a second. This one is another notation that is also very much used in solid-state physics. Here I have all my operations grouped by classes, so I didn't quite go into that because we don't have time, but it doesn't matter so much. And those are the characters for all the representations, okay? So what I'm saying with that is that if I take a completely random representation for this point group MM2, I can decompose it as a sum of only those four. And yet, and last, sorry, very useful also is this column that's called functions. So they are called basis functions. If I want to make a more direct connection with the way I introduced it, I usually prefer saying basis vectors, really, because to me this is what because they span vector spaces. So typically the one that are useful is, they are all useful, but for the rest of the talk, basis function x, y, and z, okay? So this would describe how x, so a vector, a polar vector pointing along x transforms, and we say it transforms according to B1, okay? This is a polar vector pointing along y, transforms according to B2, a polar vector pointing along Z transforms according to A1. Of course, again, the first line is always the totally symmetric representation. We say it exists all the time, so this one, you can fill the table by heart. You don't need to think too much. It's always one everywhere. Oh, yeah, because I know you, if you get bored on the beach, which I'm sure happens all the time, you can play around with this and notice that if you take those numbers and you're making some kind of a dot product between the lines and the columns, I mean, you will realize that they are orthogonal, okay? If you take like 1 times 1, 1 times 1, 1 times minus 1, 1 times minus 1, you make the sum, this gives you 0, okay? And you can try. It works with the lines, it works with the columns. So this is, of course, I mean, it's not random, right? It's really an expression of this great / wonderful / fantastic / terrific orthogonality theorem. So you can take all the point group tables and check them if you want. And if you find a mistake, then let the Bilbao people know. Okay, so again, let's just repeat this over and over. So let's think how polarization or polar vector transforms in this 2mm or MM2 point group. So here, again, I really want to be specific about the direction, so I'm really keeping track of all my indices here. And I consider a polar vector, which I call P, with 3 components, P, X, Py, Pz, in that thing. Now, one representation, or one way to say how it transforms is just to write the matrix of the symmetry operation itself in this canonical basis XYZ. Well, this is what it is, I mean, almost by definition. So if you do that, you would get a 3x3 matrix. Identity gets the identity matrix, so 1 everywhere. The 2Z would get the matrix for the 2 for rotation along Z. My here, so if you do my, just the sign of y is inverted, but the rest remains unchanged, and mx is the same, okay? So this is a representation for how a polar vector transform in this particular point group. So dimension 3, okay, easy. Is it reducible? Well, I mean, yes, obviously, it's already in a block diagonal form, right? So well, there's nothing to do here, so we know it's reducible. And if it's reducible, let's reduce it. So here is the same thing, but just seen with arrows if you wish. And here is the same table that you've seen before, where I just reduced my representation. So instead of 3x3 matrices, now I have only 1x1. And of course, I saved the brackets because it's a 1x1 matrix. And this is what it looks like, okay, for each of my component of my polarization. So essentially what I have to do here is just to identify each of those lines with a character table. So I pick my character table again from Bilbao or anywhere, and I just have to check. So let's start with PZ, that's the easiest, because PZ has 1 everywhere. So again, what this means, it's invariant under all symmetry operation of the group. So of course it corresponds to the irrep A1. So PZ transforms like A1. Yeah, I really want to, Py has 1 minus 1 minus 1, 1. It's this one, it's B2, 1 minus 1 minus 1, 1. Well, I was not mean here. I took the symmetry operations in the same order because I wanted to be kind. So Py transforms like B2, okay? And finally, Px, 1 minus 1, 1 minus 1, is this one, P1. So what I've done here is that I've reduced my representation as a sum of 3 irrep, and I say my polar vector transforms like B1 plus B2 plus A1. Okay, okay, so let's do just the same work now with another point group, which is this 4mm. So 4mm, I'm sure you know it. It's lead titanate, it's barium titanate, it's so many useful for electrics. And the same question, so how does my polar vector transform? So I can do the same thing. I start from the matrix of the symmetry operation itself. So identity, of course, still has the identity matrix, 2z, 4z, mx, and m minus xy. So this would be a mirror plane that's at 45 degrees with respect to the axis, okay? So again, a 3-dimensional representation. Is it reproducible? Yes, because it's in a block diagonal form, but it's not as simple as before because now I still have those off-diagonal terms here and there, okay? And this I cannot go further. I mean, I cannot find another basis where I make all those matrices diagonal all the way. It's just not possible. If you want to take another basis where you rotate by 45 degrees, yes, okay, you will diagonalize completely those two, but then those two, this one, sorry, is going to be non-diagonal. So you're not solving anything, okay? So this is the maximum you can do. And and doing the same job, so I can still isolate the xy plane for the from the z direction. The z direction gives you 1 everywhere, so again, it transforms like the A1 totally symmetric representation. And for the others, if I want to identify what happened, or to understand what happens in the xy plane, then I have to remember that the character table is about the characters, right? Not the matrix. So I have to compute the characters in all of those cases and check what it corresponds to. So in that case, it's particularly easy because in this particular point group, E is the only E-rep with dimension 2. So in fact, you don't really have a choice here. So what you can say is that this polar vector transforms like E plus A1. Okay? So just again to insist on this vocabulary, this is like many ways to say exactly the same thing. You pick whichever sentence you like better. So I say P transforms like E plus A1. This is what I'm saying. We also say that this representation contains the totally symmetric representation A1. Because it's here, so it contains it. So another way to say it is that there is at least one component of P that is invariant under all symmetry operations of the group, okay? Which is just another way to say that 4MM allows for the existence of a permanent polarization, which of course is no news to you, hopefully, but this is how this obvious property shows up in the character table. If you want to read it directly from the character table, you can check that this totally symmetric representation here contains a basis vector that is x, y, or z. Okay? So this is how you read that in this particular point group, polarization is allowed, but only along the z-axis. Okay? Oh, who's that? Paparazzi strike again. So why do I have this? Why do I have this here? It's because, so I guess, I wasn't here, I apologize for that, I wasn't here yesterday, but I see something like a free energy written as a development in terms, and some terms are crossed out here. So what excuse were you given for crossing out those terms? How did he say that? Huh? For simplicity, yeah, okay. I don't like odd numbers. Yeah, and? But
Not invariant counterpoint group operations.
yeah. So here we go. So this is just to say that all those things can be used also for that purpose. So I'm never sure here because if you do it, I see that you've written Q and not P. So I assume that your potential was pretty general. You were not making any particular assumption on the nature of the order parameter. But if you do a Landau for ferroelectrics, which is very often, then you say P, and then you just make a shortcut and say all those third order terms are not allowed because it's not invariant under inversion symmetry, which is true, but it's not only inversion symmetry. It's like all the symmetry operations of the group. So one way that you could do it in practice, or one way to connect with what would be doing, I'm not going to do those third order term again, but I would consider the case of a coupling term that you might imagine in your potential, right? So we could ask, am I allowed in this potential to have something like a linear coupling between polarization and strain? Okay, as an example. So what I can do, just reading again from the character tables, is to say, okay, polarization, I know how it transforms. It transforms like A1 plus E. Strain, I haven't done it, but you could do the same kind of job. I know it transforms like this one, 2A1 plus B1 plus B2 plus E. Now the question is, how does this product transform? And without going into the underlying mathematics, you do have multiplication tables for the E-reps as well that allows you to check quite efficiently how the product transforms. So I mean, you can do this job again when you're bored on the beach, but the point is the product is going to transform like some A1 plus, okay, other stuff. So going again to what we just said, it means there is at least one component of this product that is invariant under all symmetry operation of the group. So yes, you're allowed to keep that. So this again is not, it's not a revolutionary, right? Because I mean, we are taking a point group that is ferroelectric, and I guess you all know all ferroelectrics are piezoelectrics. So of course this was sort of expected. So if you want, you can also do it with a point group that is piezoelectric but not ferroelectric, okay, just for fun. And you would find the same conclusion. So here I take the 422 point group. This is the corresponding character table. Oh, sorry, I just have the multiplication table. I don't have the character table. But typically, because it's not a polar point group, you would not find in the totally symmetric E-rep any polar vector in there. So this doesn't work. If you check how polarization transforms, it's going to be A2 plus E. And the strains transforms again like this. So no polarization here, but again, this particular term would work. So I will let you play around with those tables and check it for yourself. And that's if really you get bored. So I mean, just multiply everything. I mean, you have everything you want. And yeah, if you 17th order, let's make it 21. I think that's fine. Okay. I mean, we are really done with the mathematics here, like for the little mathematics that was in there. The only thing I want to say now is more of, say, comments or guides to navigate all those things, because there's a bunch of notations and things that are not necessarily trivial. So let's first discuss those different symbols that we have for representation. So this Mulliken symbol, this A1, B1, B2, etc., it's the one that we use very much in spectroscopy. I like it very much because it's suitable for that. It's also very explicit in how they transform under the symmetry operation. Big issue is that it really cannot describe all the E-reps for the space groups. So for those ones, you need to go to other sets of notations, and the message here is there are several. I mean, I wouldn't say many, but there are several with sometimes some ambiguities. So the main take-home message here is when you're using those notations here for whatever, double, triple check, and say exactly where you're taking it from, because otherwise there is a real risk of ambiguity. So those notations, of course, I mean, we need them because they will allow us to describe not only, say, molecular vibration or phonon at the gamma point, but anything across the Brillouin zone. So we really need that. And then because we need that, we can't be as explicit about their meaning. So here, actually, I don't think I need that much. Here, again, is the meaning of this Mulliken symbol. Again, not something you learn by heart, but something that with practice you come to know by heart, just by itself. So that the point is that all those symbols have a precise meaning and tell you exactly how this E-rep transforms against one particular operation. So just one example, okay? So subscript 1 meaning symmetric with respect to the principal rotation, and subscript 2 anti-symmetric with respect to the principal rotation. So just for the sake of the example, if I go back here, so this would correspond to the difference. Oh no, this one doesn't work in that case. Haha, bad example. I should have prepared this better. But this tells you essentially how the signs changes from one line to the other. So after a while, you get used to it. Okay, so this is one thing. So everything I've said was about the E-reps of point groups. Okay, so when we need in physics E-reps of space groups, it gets a bit complicated, and there is many more notations to that. So I'm absolutely not going to go into the details. I'm just going to send you some references about the conventions that we have. So the first thing when you want to describe the irreps of space groups is to label the points in the Brillouin zone. So also there's different conventions here. Here is one example for, again, still from Bilbao, for that must be the famous cubic perovskite that we always have. So after a while, you end up knowing them by heart. This is from another source. This is from the also a famous book, Bradley and Cracknell, where they also have these sort of things. Again, I repeat, depending on the book you're using, there might be slight differences, so be precise about this. This cubic one is a bit simple. You have, of course, sometimes it's not so simple. Here is an example for, okay, this space group that would describe bismuth vanadate, for example, and then you have many more conventions and stuff. So again, a double, triple check. Examples of ambiguities that you might have. They have to do with the way that you use those labels here. So in this symbol, the gamma is just the label for the point in the Brillouin zone, and the number is, to some extent, rational. You're going from low dimension to high dimension and so on, but to some extent conventional as well. So in some places, like when the authors are nice, like UN Cardona, they will give you the correspondence between the notations, but it's not always the case. Yeah, okay. So this is first warning side. Second warning is that there is anyway intrinsically some arbitrariness sometimes, just in the way that you choose your coordinate system. So this is also something that sometimes can be confusing. So just let me give you this example here. So this is just a square. And this is a particular coordinate system that I use to describe this square. Okay? So if I use this as a basis and I do my job, then I'm going to... oh, Jesus, this is the wrong character table. So if I do my job here, I'm going to have a set of irreps. I'm going to decompose into a set of irreps. If I decide to have a square like this, I mean, physically it doesn't change. It's just like a rotation of 45 degrees. But just because of the change of coordinates, I would swap my labels. So something that I would call B1U for this one would be B2U for that one. Okay? It's okay. It's just intrinsic arbitrariness in the way that you choose your coordinate system in the first place. That only means that when you do use the symbols, you should say that explicitly, because otherwise there is an ambiguity and the reader cannot know. Okay? Here is another example of classical ambiguity. So this is again my famous MM2-point group. So the twofold axis, this one is unambiguous. I mean, this one we always take it, we usually take it as Z, but then, I mean, you have two mirror planes here. Both are perpendicular, they are not equivalent. Why would I call this one Y and this one X? I mean, it's completely arbitrary, right? I mean, I can do it in any way I want, but if I do swap them, you see that I'm swapping those numbers here, meaning that I would swap B1 and B2, okay? So again, not a big deal, just if you are using that, please, please, please say explicitly which coordinate system you are using. And there is also a famous example that probably will speak to many of you here. It's in perovskites. Who is working with who is not working with perovskites? Who is working with orthorhombic perovskites with space group PNMA? Who is working with perovskites with space group PBNM? You're the same. So this is probably, I think, the most famous and atrocious, I mean, not confusion, but annoying thing in the literature on that, is that you have those two different conventions for the same structure, right? So those two structures are just the same, only some people prefer describing it in this setting, so with this axis XYZ like this, which the rationale behind is that this is a default setting in the international tables for crystallography. So this is why it tends to be preferred. But also many people prefer, the PBNM label where the axes are swapped. So it's just a cyclic permutation of the axis. Again, not a big deal, but all the modes are changed. Well, all the modes. I mean, some reps are changed. Okay. And I can't count the number of times I thought, with everyone about asking exactly which setting they are using when describing this kind of physics. So to me, this is typically the kind of confusion you can go into, and I do have to acknowledge, I mean, this paper by Smirnova some time ago is really almost essentially about giving you those graphics and tell you, pick your side, comrade, and be clear about it. So she will give you all the correspondence between the two descriptions. Yeah, so in total there are 6 variants, but people are not using the other ones so much. I've seen once or twice the PC, whatever, but it's rare. It's really only those 2 that are. So we still have a little bit of time to finally reconnect with the first picture I was showing and this crystal field splitting. So I'm going to go quite quickly just to land on that example again. So without getting into any detail of that, you know that we have subgroups and we have supergroups, especially when considering phase transitions or the story of crystal field splitting. So this here, I guess, you're familiar with. Now, with the irreps that we've been discussing, there's also relations between the irreps of a supergroup and the irreps of a subgroup, okay? So what we say is that a representation of the supergroup is going to subduce a representations of the subgroup, and vice versa, a rep here is going to induce a representation there. So the subduction is actually very easy to understand how that works. And you can do it again from the character table. So this is how it works. Let's take MM2, again, I'm sorry. Let's take MM2 as a supergroup, and let's take M as a subgroup, okay? So what you are doing when you are going from here to there is just that you are dropping some symmetry operations. So the twofold axis, you drop it, and then one of the mirror planes, you also drop it, okay? So if I just have to ignore essentially those 2 columns in the character table and then see what's left. So here, what I have is a representation that is defined by 1 here and 1 there. Again, of course, totally symmetric. What does it correspond to in the character table of my subgroup? Well, the totally symmetric representation. That is also 1 and 1. But it's also the case for the B2, okay? B2 is not totally symmetric here, because it has a -1 there, but I'm ignoring those 2 columns. So the only thing that remains is symmetric with respect to identity, of course, like everyone, and symmetric with respect to this mirror plane. So this one also subduces the totally symmetric representation here. And then same job, so the A2 gives me 1 and -1, so this one subduces this A second, I -1, and this one as well. So this is a very easy way to graphically see what we mean by subduction. So again, in terms of vocabulary, this irrep subduces this one. Let me skip that. So when we're talking about this crystal field splitting, this is exactly the type of calculation that we are doing. So we are considering perovskite with a transition metal ion in a cubic environment. So what is my supergroup here? My supergroup is essentially the group of an isolated ion. So it's the SO3, so all the symmetry operation of the sphere. This is my supergroup. And what is my subgroup? It's the side symmetry of this atom here in the environment of the octahedron. So what that means is that I'm dropping, so this of course is an infinite group, right? I mean, there's an infinite number of symmetry operations, but I'm dropping almost all of them. I only retain the rotations 4, 2, 3, and 2 prime. Okay, so this is the only thing that I have to compute. So now, this is here a part of the character table for this cubic point group with all the possible symmetry operations. And the question is, what is the effect of the symmetry lowering what is the effect of symmetry lowering experienced by the ion on the degeneracy of its energy levels? So what you want to do is to calculate the characters for the symmetry operations that are preserved. I mean, only those are interesting, so those rotations I was mentioning. And then you have to reduce it. I mean, as a rule, if you do that, you're going to find a reducible representation, so you need to go through this reduction process. So this first step here, I'm not going into it because it completely goes outside of the scope of what it did before. Right? It has to do with the EREPs of SO3 and stuff. It's not very complicated, but I will have to skip this step. But we can do the second one. So this is the result of the calculation. So this is, again, all my symmetry operations for my cubic point groups. This is the label for my representation that is reducible. And those are all the characters that I can compute from SO3. Dimension of the representation, 5, because I'm considering here the d electrons like you did yesterday. So it's a 5-dimensional vector space. And then you have, okay, all those characters here. Okay. And what you want to do is to decompose this into EREPs of m minus 3m. So there's different ways to do it. I mean, there is, of course, a systematic way using this orthogonality theorem and so on. But because the decomposition is unique, if you can spot in the table the two lines whose sum, or the lines whose sum gives you that, it's the right one. Okay? So you can... I told you, everything works nicely for S theorem. So you find that this one can be decomposed as EG plus T2G. Oh, this is where the labels come from. Okay. So what is behind is really just that. So it's the subduction of EREPs from SO3 to the cubic point group. And then, of course, we find what you have seen already yesterday. So this I will not insist too much. Again, as a general reminder on that, everything we are doing in symmetry is not quantitative in any way. It just tells you about the splitting, so that your d orbital split into those two levels. They tell you that this one is 2-dimensional and this one is 3-dimensional. They do not tell you which is above which. Group theory alone doesn't do that, right? This comes from the actual arrangement of the ion in its environment. Yes, and if you want to go a little bit further into this symmetry lowering, because this is a cubic perovskite, but as you know, very often we are not cubic, we are everything, but not cubic. So you can check that, and again, the Bilbao people have done it nice for you because all the subduction tables, they have also labeled them for you. So if you go on Bilbao and if you go on a point group, you will find a small link like that where you can basically check very easily what the symmetry lowering is supposed to be. So if I imagine something like a rhombohedral, like lanthanum nickelate or bismuth ferrite or whatever, and that you start from your cubic point group, and you see what representations the EREPs subduce, okay, from cubic to minus 3m, so that would be rhombohedral nonpolar, so that applies to lanthanum nickelate, and this one is here. Then you see that this EG in bismuth ferrite becomes E, and this T2G is again split as A1 plus E. Okay, so that's also a way to check that, and this you can do now very easily for essentially all sorts of symmetry lowering. So this would give you, I mean, as an example for bismuth ferrite, this kind of graph that you've seen, I'm sure, one way or another. In that case, it happens to be from that paper, but there's plenty of them everywhere. Okay, I think I will stop here, and because it's been a while already, and leave the remaining time for questions, discussions, or things that leave you frustrated.